In a previous video, I assembled this modern recreation of the Heathkit ETA-3400, a memory and I/O expansion accessory for the Heathkit microcomputer learning system. This modern recreation was designed by Dr. Scott M. Baker, and I'll provide links to his YouTube video and GitHub in the video description. In this video, I want to tell you a little bit more about the device that inspired this board. I'll tell you how I programmed the two programmable devices on the board that are required to make it functional, and then we'll put the final unit through its paces. Here you can see an example of the ETA-3400. Inside it had sockets to expand the RAM available to the microcomputer trainer, some additional ROMs including a serial monitor and a version of Tiny BASIC, and on the back it had a tape input, tape output, and RS-232 serial port. Finally, on the back there is a US power socket. You would sit your Heathkit microcomputer learning system on top of the ETA-3400 and connect them with the supplied ribbon cable. The switched power socket would allow you to turn both devices on and off at the same time. I do wonder if there are any examples with a UK power socket, because they were certainly available in the UK. In this video about the ET-3400, the legendary Tim Gilbert flips through his 1984 copy of the Maplin catalogue. On the right-hand side, you can see the microcomputer trainer sitting atop the expansion unit. In the UK, the trainer itself retailed for $189.95. As Tim is pointing out, the ETA-3400 expansion unit was also available in the UK from the Maplin catalogue with a retail price of $149.95. Despite this, I've never seen the expansion unit come up for sale here in the UK. If we look back at this eBay listing, we can see this particular unit is being sold as a set for $485.95. This particular sale isn't available for shipping to the UK, but as you can see from the related items along the top, it's fairly expensive to ship these units across the Atlantic. This is typically in the range of $100 to $150, but as you can see, some sellers seek shipping costs north of $300. Now, when these items finally arrive in the UK, they're often hit with additional taxes and charges, which puts the overall cost of such items outside of my price range. So let's see if we can finish up our work on Dr. Baker's recreation. As I mentioned, there are two chips that must be programmed to make the device operational. To configure those chips, it may be possible to use a universal programmer, such as these popular ones from XGeku or one of their many clones. Now, unfortunately, I don't have one of these, but what I do have is Arduinos coming out of my ears. So I figured someone somewhere online must have figured out how to use one of these to program one of these. After considering various different options, I settled on TommyPROM, an Arduino-based EEPROM programmer. One of the things that attracted me to this particular project was its simplicity and the fact that it was designed to be built on a breadboard. So here's what my programmer looks like. As you can see, it's a little more messy than the original design. Now, the Arduino doesn't have quite enough pins to address the entire EEPROM at once. To get around this, TommyPROM uses a pair of 74 LS164 shift registers. Unfortunately, I didn't have any of those to hand, but TommyPROM also supports the 74 LS595, and those I do have. The last component I need to install is the 28C64 EEPROM right here on the breadboard. Next, we need to install the TommyPROM software on the Arduino. I've already gone ahead and downloaded the code and set this up ready to install here. All I need to do is plug in the Arduino and press upload in the IDE. As we can see, the programmer software has now been uploaded to the device. Next, we need to connect to the programmer. We do that using a serial terminal. Here I'm going to use Minicom. You can see we're now left with a prompt. If I press enter, we'll see the options available to us. TommyPROM lets us dump the code that's currently on the EEPROM. We do so by typing D and the address we'd like to see. Let's start at 0. As you can see, the EEPROM already contains some code. So for completeness, I'm going to go ahead and erase it. For some devices, you can use the E command and specify a start and end address. Unfortunately, this isn't supported with the Atmel devices. Instead, we can fill the device with hexadecimal FF bytes. We do this with the command F, the start address, the end address, and the desired fill byte. As you can see here, the write has failed. This is a common problem with used Atmel EEPROMs like I have here. However, it can also afflict new devices. Assuming the programmer is otherwise wired correctly, this is usually caused by the chip being locked. Fortunately, TommyPROM can unlock the EEPROM. All we have to do is type U at the prompt. Now we can retry the fill command on our device. For some reason, TommyPROM always seems to lock up once I've used the fill operation, but we can always reset it at any time using the reset button on the Arduino. We can verify the result, however, by using the blank check command. As you can see, the block was successfully erased. We can also inspect the data by using the dump command as before. And as you can see, the EEPROM is now filled with Fs. To write the firmware, we need to use the write command and specify a start address. When we press enter, we'll be asked to provide the binary data to write using the X modem protocol. And to do so, we use the send option in Minicom. Here, I select the X modem protocol. I can go to the ROMs folder, and I can select the combine.bin provided by Dr. Baker. As you can see, the write has now completed and the data has been written to the EEPROM. Again, we can inspect it using the dump command. We can also read back and save the data by using the read command. As we can see on screen, there's 5 kilobytes of data. So our read range is from 0 to 13FF. Again, we use the X modem protocol. I'm going to save the file as verify.bin in the ROMs directory. We can now exit Minicom to verify the data. We can inspect the data that we read back using the xxd command. This provides a hexadecimal and ASCII representation of the data in the binary. We can compare the two binaries using the diff command. As you can see, there is no reported differences between the data we wrote to the EEPROM and the data we read back. This indicates our EEPROM was written successfully. We can now unplug the programmer and remove our freshly programmed EEPROM. For now, I'm going to leave it on the trainer's breadboard for safekeeping. Next, we need to program our programmable logic device. And again, I was looking for an Arduino-based solution. The tool I settled on is called Afterburner. But as you can see, it's more of a PCB-based solution. Fortunately, it also started out as a breadboard programmer. For this reason, I'm using the version 4 legacy code. If we look at the schematic appropriate for our chip, it's much simpler. An Arduino, the programmable logic device, and a few resistors and capacitors. The only additional complication is the requirement for a higher voltage to program these devices. For this reason, Afterburner also requires a boost converter module that can generate these higher voltages. So this is what I came up with. As you can see, it's small enough to squeeze onto a breadboard Arduino shield. All I need to do is put the programmable logic device into the breadboard just here. So let's plug in the Arduino and upload the Afterburner code. Unfortunately, my boost converter module doesn't break out the enable pin. As a workaround, I've gone ahead and connected the input voltage to the VPP programming pin on the Arduino. To allow time for the programming voltage to stabilize, I've extended the delay in the set VPP function from 10 milliseconds to 100. Now we need to upload the code to the Arduino. While Afterburner also uses a serial interface, it's controlled by a companion program. For some operating systems, there are pre-compiled releases in the releases folder, but you can also go ahead and compile the program yourself. Here I'm using OS X, so I use the compile OS X shell script. This compiles the binary Afterburner_OS X. These are the commands we can send to the programmer. To make sure everything's working, let's try and read the device info. First, we must set the device type we're trying to program. We also need to tell the tool which serial port to use. Finally, we can specify the I command. As you can see, we've correctly identified our programmable logic device. Now let's go ahead and read to see what's on the IC. As you can see, this device has also been used. It's important to erase the device before we try and use it. Now when we read the device, we should see all ones. We now need to program the GED file provided by Dr. Baker using the write command. No errors were reported, but we can verify the data by using the verify command. No error has been reported, indicating the data has been verified successfully. As a casual check, we can also read back the data to make sure we see that the pattern has changed. As we can see, the pattern has been updated. We can now unplug the programmer and remove our freshly configured programmable logic device. Now we've programmed our ICs, let's install them in our recreation of the ETA-3400. Before you can use the accessory, there are a few modifications that need to be made to the microcomputer learning system. For this purpose, Heathkit provided a modification kit. For the original ET-3400 model that I have here, you're required to install the 4 MHz crystal. As you may have seen in my previous video about the trainer, that upgrade had already been performed by the previous owner. In all variants, you're required to install the 40-pin header that you can see here. Again, that's already been done on my device. Finally, as the accessory provides the memory in the combined unit, you're required to remove the RAM from the front of the trainer here. Before connecting the board, we need to make sure all the jumpers are in the correct places. Jumper 1 is used to configure the programmable logic device. It's currently unused and actually can be left disconnected. In this case, I've connected it to ground, but there's a 10K pull-down resistor here that does that anyway. Jumper 2 sets the baud rate. We'll look at that more closely in a moment. Jumper 3 configures how the device gets power. If a jumper is installed here, this recreation board will pull its 5-volt power over the ribbon cable connected to the trainer. Jumper 4 determines how the Raspberry Pi gets its power. If it's connected, it uses the power that's coming from the board. As we're not using a Raspberry Pi right now, it doesn't really matter. Jumper 5 sets the cassette gain. I currently have mine configured to 500 millivolts, but you can set it down to 50 millivolts if that's more appropriate to your cassette recorder. Jumper 6 provides a built-in option to configure a null modem cable. In normal operation, they should be jumpered directly across. To configure this as a null modem, simply rotate the jumpers by 90 degrees. A very clever design decision by Dr. Baker. Finally, Jumper 7 determines whether or not we're using the MAX 202 chip here to drive the serial port. If you're using a Raspberry Pi, you want to disconnect these to allow the serial data to go to the Raspberry Pi header. To set the baud rate, let's have a quick look at the schematic. As we can see, there are various options we can use. I've decided to use 9600, which is the fastest baud rate available. To set this, we must connect Jumper 2 and Jumper 3. Jumper 4 must always be connected. To connect the devices, we use a 40-wire ribbon cable with standard IDC connectors. This is the same type of cable that was used to connect IDE hard drives and optical drives to desktop computers. Pin 1 should be connected here on the connector. This is very important because the cable connects the power between the devices. Pin 1 is connected to the left-hand side as marked on the PCB on the trainer. Now let's power up the computer and make sure it still works. As you can see, we're greeted by the familiar CPU up message, even though there's no RAM installed in the trainer itself. This indicates that the accessory is successfully servicing memory requests from the CPU. The new ROM also contains a memory test program. In addition to checking the RAM, it will also indicate that we can access data in the external ROM. The memory test program is at 1A34. The test program indicates the largest identified RAM address on the first 4 displays. In this case, we can see 0FFF, which is the full 4K. On the final 2 displays, it indicates the value of data it's writing and reading back from each memory cell. If it encounters an error, it will indicate the address of the faulty memory on the first 4 displays and the data that caused that error on the final 2. The program loops forever, so it can be used as a burn-in test. I'm going to let this program run for a while to make sure everything's functioning correctly. But when we come back, we'll try out a few more features of the ETA-3400. I've let this test run through several times now with no indication of any faults. So I think it's reasonable to say the memory test passes. Now let's reset and see what other things the ETA-3400 can do for us. In my previous video about the microcomputer learning system, I was interested in finding ways to save the programs we'd spent all that time entering. The ETA-3400 includes tape input and tape output jacks to allow us to store our programs to tape and to play them back into the computer. While the original device uses RCA phono jacks, I've decided to go with 3.5mm sockets instead. Off camera, I've recorded a couple of the sample programs to this audio cassette tape, so let's see if we can get the computer to read them back in again. To load from the cassette, we need to use the new cassette loading routine in the external ROM. The manual provides the start address of the routine, the memorable 1ABC. If the loader encounters an error, it shows the word error. If the load completes successfully, the monitor resets and shows the CPU up message. During loading, we saw the decimal place flashing. The program we've loaded is sample number 4 from the Heathkit manual. As you can see, the program starts at address 0000. Let's try and load another program from the cassette tape. Again, we see the decimal place flashing. This program is an old favourite, sample number 5, the number guessing game. It starts at address 0060. We press a button to set the random number, and then we begin our guesses. The other major piece of functionality is the addition of a serial terminal. This allows us to control the computer using a regular display and keyboard. The ETA-3400 has a 25-pin female serial port on the back of the device. So I've finally found a use for this old serial modem cable that I've had safely stashed away for the last 20 years. I've connected the other end to my Mac using this cheap RS-232 serial to USB cable. We'll use Minicom to connect to the computer. If you recall, we configured the ETA-3400 to use 9600 baud. We'll need to configure Minicom to use the appropriate settings. Here we'll press C for 9600. The ETA-3400 uses 7-bit data transfer, so we'll also press R to configure the settings correctly. To hand over control to the serial monitor, we need to execute the code at hex 1400. To do so, we press do 1400 on the keypad. As you can see, we're greeted by the monitor prompt. The user manual contains a monitor command summary. For example, we can press R to display all the registers. You'll notice that didn't work. The serial monitor requires capital letters, so let's enable the caps lock key and try again. The monitor displays the value of the registers. We can also inspect memory by using the D command. This is the ticker tape program we loaded in from the cassette. We can modify memory locations using the M command. If we don't want to change the value, we can simply press Enter. An invalid entry will exit this part of the monitor program. We can redisplay these memory locations to ensure they're unchanged. We can execute a program using the G command. Let's try the ticker tape. To return to the monitor, we have to reset the device and press do 1400. As you can see, the monitor resumes. Let's speed up the ticker tape. The relevant byte is at hex 24. Instead of 60, let's set this to 30. Now let's run the ticker tape program again. As we can see, the ticker tape is now much faster. Let's get back into the monitor. One interesting feature of the monitor is the ability to decode instructions. To do so, we use the I command. Here we started from address 0. This provides a hexadecimal listing that matches the format in the user manual. We can save blocks of memory to the terminal or papered tape using MICBug or Motorola SRAM format. This uses the P command. This is the ticker tape program. We can also save data to audio cassette using the T command. The data is first encoded using the same Motorola SRAM format. It's then modulated into an audio signal using the Kansas City Standard or byte format. One powerful feature of the ETA-3400 is the addition of Heath or Pittman Tiny BASIC. To use Tiny BASIC, we must first enter the serial monitor, also known as the Fantom 2 monitor. Once there, we must execute the code at hex 1C00. Here you can now see we're at the BASIC prompt. Here I've entered a simple program that prints hello world 5 times. Tiny BASIC doesn't have the for next construct, so I've had to use a variable in combination with an if and goto to form the loop. The full list of keywords is shown in the manual. As you can see, we can save and load programs, so let's give that a go now. To save the program, we're going to need to connect the audio out to the microphone socket on the cassette recorder. And pause the recorder and set it to record. Now we type save and give the program a 1-character file name. We resume the recorder and press enter. We can exit BASIC by typing by, and this will return us to the serial monitor. If we re-enter BASIC with the B command, our program will be preserved. However, if we re-enter from hex 1C00, the program will be wiped. Let's see if we can reload the program. First, we need to change the audio cables. Next, we need to rewind the tape. Now let's try reloading our program. We can review our program by typing list. And we can run our program again by typing run. The ETA-3400 significantly extends the capabilities of Heathkit's microcomputer learning system, and this recreation by Dr. Baker has been loads of fun. If you happen to have an ET-3400, I'd strongly encourage you to consider extending your system with this very board. But if not, I at least hope you found these videos interesting, and I hope to speak to you again soon in the next video.